Hey everybody, welcome back to another JetBrains Rider live stream. I'm Khalid, if you didn't know that. And I'm really excited about today's guest. But before we introduce them, like always in all these JetBrains live streams, let me do a little bit of housekeeping, just so you know the rules of engagement here. So, if you're watching us live right now on YouTube, which I see a lot of you are in chat, thank you for joining us. That's very cool of you. If you are in chat, feel free to ask any questions during this entire live stream. I'll be kind of gathering them up for our guest, and we'll be asking them live here on this stream. So be sure to think about what you're hearing and ask any questions that you're curious about. A question that always comes up, life happens. You have kids, you have dogs, stuff just happens. So if you need to step away, this live stream is being recorded and available on JetBrains TV. So if you want to come back, watch this, rewind, do anything with it, feel free to come back, subscribe, hit that notification bell on JetBrains TV. And yeah, you'll be able to see this content and any other content that we have on the channel. So on that note, housekeeping is done. I'm really excited about today's guest. I consider him kind of one of the .NET heroes of our community. I was just joking with him that he has over 7,000 blog posts on his personal blog. So if you want to catch up, you probably have to start writing right now. So without any further ado, I want to welcome Oren to JetBrains TV. And yeah, welcome. Really excited to have you here today.
So am I. Thank you for having me.
Yep. So I'm going to give you the stage right away. I'll be here quiet. If you need anything, just let me know, Oren. And I'll be watching the chat for any questions. So folks, feel free to ask. Oren, stage is yours. Good luck.
All right. Thank you very much. In general, by the way, feel free to ask questions. We'll try to answer them as soon as possible. My talk today is going to be about building a database engine in C#.NET. And it's interesting because for a lot of people, especially in the database community, when you start talking about, oh, you build a database in .NET, that seems like a really strange thing to do. And the nice thing about it, I've been building databases for a lot of time. I actually went and looked, and the first database I wrote was something in the order of 2005, so almost 20 years at this point. And here is my blog, and please read. I would appreciate that. Now, let's talk about database engines, and especially database engine in C#. For the most part, when people think about a database engine, about system software in general, they think about, oh, stuff that is written in C. I have to get every little bit of speed out of the system, right? So the interesting thing about it is there are quite a lot of databases that are written in many languages. And I've written here some of the most common ones in Java. There's also quite a few written in C#. Most of them are not open source, however. But a really interesting aspect about C# is that it is actually a really, really, really good language to write databases. And the reason for that, it allows me to express ideas at multiple levels of abstraction at the same time. On the one hand, I'm able to write really a high-level functional or whatever code, and if I want to use a language integrated queries, I want to use a class hierarchies, whatever. I have a lot of power in my hand, and really, really a lot of expressiveness. Record, pattern matching, records, all of those sort of things. At the same time, I'm able to say, hey, for this particular bit of code, I'm going to need to control the memory allocation, the alignment, go as deeply as I would go if I was writing C. But the nice thing about it is that I don't have to do it all at the same time. If I'm looking at a language like C, which is an amazing language and 50 plus years in the industry, but I don't have a hash map there. Actually, I can go to a third party, there are a few of those, but the actual language design means that I don't have the hash map. If I'm using Python, then I have really good high level stuff. I cannot write high performance low level code. Use C to do that. C# is one of the few languages that actually lets me do both. But, and this is really critical, I can do that at a really simple boundary. So I don't need to accept, oh, I'm going to use only high level code in this project or even this class. I can mix as much as I choose, and this is amazing. Now, I started being in RavenDB in 2008, and it started as I just had to get it out. So I started just writing standard C# code, and the first version of RavenDB was pretty much a C# web application using ASP MVC. So again, we're talking about close to 15 years back, 16 years back. And it was really good. It allowed me to actually deliver a whole database engine in a relatively short amount of time. But that came with its own cost. When we started pushing a lot of data, a lot of requests, we started to notice that we're hitting a hard limit of what we can do. In particular, the more load we put on the system, the slower things became. Now, obviously, the more load I make, the slower things became, because there is a finite amount of CPU power that I have. But we started profiling the system, and we realized something really, really nasty. 85-90% of our time was spent in garbage collection, which means that I'm actually able to hit really high numbers in terms of performance, but I hit a limit, and the limit is because I'm only using 50% of the CPU utilization. This is just clean up garbage. And that was insanely frustrating. Now, the underlying reason was actually very simple. We allocated too much. If we allocate too much, then the garbage collection has to come and clean up after us. Okay, fine, that's not unexpected, but we could not clean it up. Try to imagine how often do you have a new in your system? Are you actually paying attention to every single new? So that was obviously a huge issue, and okay, this is the limitation of C#. We cannot do anything beyond that. We actually sat down and thought about, okay, how do I write this? How do I fix this in such a way that we could still move forward? And the idea was that, okay, I don't want to switch technology. I'm gaining a lot of benefits from using C#, from being familiar, from the I think that's something that people don't really realize, the level of support of scaffolding that you get from using a managed language. And I'll give you something trivially simple. You have hit a null reference exception in your code. That is 100% guaranteed. And when that happens, what do? In most cases, the way that it works goes like this. Okay, I get an reference exception. I look at the stack trace. I go to the method. I say, I forgot to add a guard there or something like that. Okay, that's annoying. I will fix that. And then I hit F5, and in a couple of seconds, I'm back and running. And the nice thing about this is that the flow that we have here is so good that I'm not usually even bothering to walk around that. It's cheaper for me to run, hit the error, fix it, and move on than try to predict all of the error upfront. Compare that to using something like C++. Oh, you hit another first exception? It's not another first exception. It's an invalid memory access. And you know what the fun thing about that? It crashes the process. And you know how you debug that? Well, you look at memory address locations, and maybe you're lucky enough to be able to attach a debugger and get a stack trace, but mostly you don't. And you basically, dispel and kill stuff and then look at the code and try to figure out what's going on. I remember the first time I actually started using C#, and we were talking about 2001, 2002, I wrote this exact scenario. And I have an RF exception here with stack trace, and I have an access violation error and at some hex address. So I really want to keep using C#, but I need to be able to get the speed that I want. So let's see what we did. C# always had good foundational story around low-level stuff. Pinvoke, native memory, those sort of things. And we started getting more and more of that over time. And in 2015, something amazing happened. Coincidentally, also the time that we hit the wall with the old code base. It went open source and it started running on Linux. And suddenly I could go and say, this method, for example, if we look at StreamReader allocate two buffers, a 4 kilobyte byte array and a 1 kilobyte char array, or 2 kilobyte char array, something like that. And that means that if you're allocating a lot of stream readers, you're allocating a lot of memory. And now you have to understand the process in which this works. If you accept a lot of requests and you process them using StreamReader, well, okay, that's a lot of allocation. The request may take a while, during which we'll hit a GC cycle or two. The memory get pushed to Gen 1, and suddenly you have a lot of memory utilization, most of which is just garbage. I can go and fix that. Or I can go and rewrite the way that I'm reading data from the network. Other things that happened is in terms of what you can do with C# in general. Span has been a godsend. We had to write our own span from let me check. So this is my original span. And this is originally written in 2013 or so. Okay, so we can see we have quite old code base in this case. And but now we have span, and now we can start writing things around that. And how intrinsic we touched later, but basically suddenly the platform for building systems for building databases became so much easier. So I want to write something simple, and I decided I'm going to write a Redis clone in C#. Just to give you some example of how it works. So here is the logic. You can see I'm starting listening to the network and accepting a client. Then I'm handling the connection in an async manner. That's good. Okay. Let's move to the next stage. Okay. And I want you to look at what I have here. I have some stuff about handling the connection. Then I have execute command. Then you can see that this utilizes the Concord dictionary to store and retrieve strings. I have the link for that in the presentation. You can see the whole thing is under 200 lines of code. And this is an absolute killer, because try to imagine how much requests per second can I run on this? What do you think? And the answer is that this stupid silly code that was literally written in the most obvious manner hit just under 1 million reads and writes per second. So 1 million operations per second, which is an absolutely insane number compared to the amount of effort that I put into that. And I will touch a little bit later on why this is such an amazing aspect, because I could not do the same thing in C. Redis is actually written in C, and it is single-threaded. So if you want to run a Redis that would utilize all of the cores that you have on the system, and for reference, on this system I have 12 cores, I would really like to be able to use them. You cannot do that with Redis. With Redis, you have to run 12 copies of the software, and then you have to be able to communicate between them. Now you have a much more complicated system to deploy, to run, etc. With this, it's just this, and you have 100 million records per second. Now, why is that? Why is it so hard in C? Because you have to deal with memory, and you have to deal with memory on multiple threads, which leads to such a huge mess that is absolutely insane. So let's go and talk about a little bit deeper. So this is the full code, and I will throw that in the chat so you can see how this works. And I'm sorry, not 200 lines of code, 100 lines of code for the whole thing. You can see here, every time that I handle a connection, I'm opening a stream reader and stream writer. This allocates some memory. Again, I'm doing the absolute least amount of work that you have to do. 1 million reads and writes per second. Now, if I want to push it a little bit higher, I can expand it from 100 lines of code to 300 lines of code, and I exceed 1.25 requests per second, million requests per second, at a response time of 40 milliseconds for the 100% line. Think about the implication of that. If I wanted to spend, a month on optimize everything, I can actually get to a much higher level. I can probably exceed the performance of Redis by a factor or two. Again, mostly I can use threads, and I can use, I can do anything in C# that I can do in C. So now I want to show you some of the things that you can do in C#. So what you see here, this is me controlling the placement of values inside the struct. So I have a very good control over the exact memory layout that you're seeing. And just this thing means that, suddenly I can start, you see here, it means that I can control what cache line this is used. So I can ensure that two values will not share the same cache line, and therefore will not conflict with one another. I can use here, and these are the hardware accelerated values. And we see a lot of that in just a little bit. I have native memory, I have a lot of stuff like that. Those tends to be stuff that you need because you have really, really strange things that you need to do. But when you actually need that, that's absolutely amazing. Absolutely amazing what you can do. So now let's talk, before we move to showing more evil stuff you can do, are there any comments to address?
Yeah, I guess people are asking for that gist link just so that they can look at that code. But other than that, what's fascinating? You're right. Like, I think 99% of folks who write C# probably think about classes in terms of logical structure and just being objects in memory. But it is really nice to be able to work with structures and how things are stored in memory when you need it. So I think that's really amazing stuff. So other than that, no real big questions. So I'll let you continue.
Okay. So the next aspect of C# that I want to touch is the just-in-time compiler. Now, the just-in-time compiler is an amazing technology that take your code at the actual host machine and compile that. Now, again, I'm comparing to C, it also does that. What's the difference? Well, the major difference is that in the case of just-in-time compiler, it's going to compile that for that specific machine that you're running on. So again, if I'm looking at my machine, you can see that this is a specific Intel CPU. It has specific features. I can even optimize for the specific sizes of the CPU caches. So suddenly the compiler that we have has a lot more information about what you can do. For that matter, I can do a whole bunch of tricks around that. So let me show you a couple of interesting tricks. So here I have some code. You can see that I'm reading an environment variable and putting that in a static read only value. And here I have this thing. Now take a look at this piece of code. And let's think about what's going on. A static read only value is a constant, but it's only constant at runtime. But the nice thing about it, the GC can use that information. So I initialize this value, and this happens in the logger static constructor. And then when we call the run method, the GC is going to say, okay, I'm going to call the write method. But I can see that the write method has enabled, and I see that enabled is a static read only, which is set to false. If it's set to false, then it just returns. So what it will do, it will actually remove entirely the logger write method. And then it says, oh, you know what? I'm looking into this and I can see that the v2 string isn't called. So I'm going to be removing that as well. And then it's going to say, hey, you know what? I can see that the for loop here isn't actually being called either. So does it have an effect? So it's removed that entirely, and suddenly this method becomes empty. And it sounds funny when you look into that, but try to imagine, okay, if I have other stuff like this, suddenly the logger write is being entirely removed. And the code is being optimized for my machine, for my scenario, for my behavior. Not because I wrote a lot of if-defs, just because of the way that I structure the code and lean on the JIT. Now I'm going to show you some pretty scary code. I want to have you guess what language is this. Oh, I see that I already told you what language is this. Okay. But if you had a chance to look at Rust code, you will see that this is a very familiar to how you write natural Rust code. But again, this is C# code, and this C# code does something really interesting. Type of flow, range exclusive. And I want to show you the actual code for this and what it does, and then explain why. Term numeric. Okay. So you can see we actually have a bit more items here. And blah, blah, blah. And now we're doing something quite interesting. All of this thing, this, for example, this is happening at G time. So this is actually super cheap. But the thing that is most interesting for us is it? Okay, I need to find it. I'm sorry. Okay, so now let's look at this. What you can see here is this piece of code. If Tilo is exclusive, then call this and this. If not, this just gets skipped. So why does this matter? This happens a lot, like lots. And this is part of a piece of code that is being run billions of times per second. And the idea that I can utilize G to remove that means that I can get tremendous benefit in terms of performance. Let's see where this actually gets used. So we have this location, which we find. Okay. So now you can see where we are actually. Again, I'm sorry, the code isn't trivial, but you can see how we are passing this. If this is greater than, less than, etc. Now, the interesting about this is that we get a query from the user. Based on the query, we have one implementation that gets specialized at G-time. And then this thing is being called, this multi-term match, is being called billions of times in order to compute the end result, which means that it's a huge benefit for us to remove even a simple check. Remove the code, remove this, and you have a measurable performance impact. So that has a huge impact. Now, I want to show you another aspect, and we have it here. So one of the things that I have to do, I have to compress and decompress numbers. And in order to do, not this thing, second. So let's talk about what we have here. Here we have an input buffer which contain 256 numbers. And I want to pack them from being numbers that take 4 bytes each into some number of bits per this. So I'm going to call this value. And here is the buffer. And again, I'm using pointers, a native code, etc. And then I have this thing. And then I have this amazing piece of code. What this says is I want you to pack from the input array into the output one bit from each of those into the output. So I'm getting a list of 256 integers. And again, let's do the math. 1 kilobyte of memory. And each of them should output 1 bit out. So that would be 256 bits or 32 bytes. And etc. for each one of those. Now let's look at how this actually looks. And what you can see here is that I'm using vector instructions, and this generates a SIMD code. SIMD stands for single instruction, multiple data. By the way, this is an algorithm that was invented or developed by Daniel Emir, and he wrote that in C, and you can see some of the notes that we have about the transformation from one side to the other. And this matters because this is relatively simple code, at least if you understand what it is doing in terms of vector operations. But I'm going to show you what this actually does. So you can see here is the thing that we're running on. Here is the shift left, etc. What you see here is the set of assembly instruction that we talk about. So you can see that I can go here and do, here is the OR that we have here. And here is shift left, which is this guy, etc. Now, the reason this matters is that look and consider the impact of this on my system design. I'm able to write C# code and control what sort of assembly instruction are being generated for that. I'm able to actually take advantage of an algorithm written for low-level C code in really, really nasty C code again. And at the same time, I'm able to say, oh, you know what? I'm generated appropriately. For that matter, let's look here at the bottom. Here you can see that the encoder is a mask. And that would be this, effectively this function. So this is a really interesting aspect to talk about. Let's talk about this. So we said we can do a type low and then this, and say whatever, redact this or not from the compilation output. But let's talk about this really nice trick. So here I have a struct that is generic over T transform, and I'm specifying this lovely thing. T transform is a struct that implements an interface. This case here it is. Now, when we want to compile this piece of code, where it is here, this piece of code, then the JIT is going to run over this and says, hey, I know that in this case, this is use mask entries. I know that mask entries is a struct. Therefore, there is no overload possible. There is nothing that I need to do. So I know at compilation time exactly what the method that I have here. So I can take that method and inline that into the system. And if I have more interesting things to do, such as I can control, or if I'm passing you what is it? If I'm passing you a value, let's do this. We'll be able to see it here. Now, let's see what we have here. We have the sim transform. Absolutely. Now let's look what happens. I'm saying here's an if statement. And here's this method. And the entire method is gone. The entire method is gone because now this guy is, oh, I know that this is false. So I can say at the G time that, oh, I can just return for this. Now, this sounds like a pretty meaningless feature, but it means that now I have a really interesting way to parameterize my code. If you're familiar with how you write C++ code, and you may have code that is parameterized to certain levels. Oh, I want to have to pass 3 here, or something about, oh, I have a buffer size that I know at compilation time, but the code should be agnostic to that. So I pass it as a template parameter. This means that I can do the exact same thing in C#, but in a much, much simpler manner. Now, you can also do this in other places. Now, this is actually something that we use a lot. As you can see, look, every time that we have a struct. So here we have, no, I don't know this. Okay, here. Okay, so again, look at this. This is an encoder for a piece of data that we have, which is super low level. And again, this is the sort of thing that happens many, many times a second. Many times, this case referring to many billions. So now I can go and says, oh, and in here I can make determinations based on that. And all of that is being elided or removed. There's other things that I can do. Where is it? There is some around here that we have expected constant. That would be in one of the things that we do, which is expensive, is parsing JSONs. So let's see how that looks like. When we accept a batch of commands from the user, you go here, and one of the first things that you're doing, we have to parse them. Here we go. Batch command parser. Again, this is when we have to basically get JSON from the user, and we have to translate into this. And as you can see, this is a really, really rich system. Lots of operation, lots of things. It's really hard to do that. So what we have done, we started writing super low-level code. And here we are reading the data. We are reading the data as unmanaged buffer. And at some point here, we have this guy. And I wanted to look into this sort of code. So what we have here is basically, let's go over all of the properties that we have in the system. And we're saying, okay, here I have a state, and here have the state string size and the string buffer. Now, this is a really interesting observation, because is memory equals. And apparently, okay. So what's happened now is this is the sort of code that I generate. And I'm not going to go into exactly how it works, but what this basically does, it takes advantage of the fact that I know at compilation time what the size of the string is, which is then get pushed into this, because this is being read as a constant. This get pushed down and down to the level that, oh, I need to do that using this comparison, or eventually you can see this is the sort of code that would be emitted for that comparison. Now, this is not something that we recommend for the faint of hearts. This is the sort of thing that you want to do when you want to squeeze every little bit of performance of the system. But at the same time, in the exact same system, I have stuff that run, once a minute, once a day. I can go and write high-level code. So let's look at debug admin handler, for example. Okay. So here's some code. I'm using link here. Now I'm using multiple links here. And the nice thing about it, you can see this is debug endpoint. It happens every once in whatever. This is only being called for troubleshoot. I don't care about its performance. So I can write code that does go by, and from a performance perspective, this is absolutely horrible. I don't care. The code is simple, clear, and obvious. I can just run with that. And that is really nice thing to do. Now, I want to talk about one other topic, which is a huge, huge topic for me. And this is that C# is a managed language. That means that I have automatic memory management, I have a JIT, reflection, all of those sort of things. So far, I spoke a lot about the JIT, about being able to use native code, memory, etc. I want to talk a little bit about the GC and how it works. Now, there is a really nice book by Conard, which is about 1,000 pages, about this big, that talks about how the GC works. It is absolutely packed with information that you hope to never want to have. Like, you really don't want to know any of those sort of things. But if you do know them, that means that you can start doing a lot of really, really crazy stuff. Earlier I mentioned that one of the things that C++, I said, oh, so we have the book here. Yeah, just for comparison how big it is. And by the way, an amazing book. I recently had to go and figure out how the GC deals with cross-generation pointers, and I found the relevant section in like 2 minutes. And I have multiple copies of these books in the office. So the idea about this is that what can you do with the GC? Well, you can ignore the pointers. The name of the book is Pro.NET Memory Garbage Collection or whatever. Yeah, really good book. Don't read it for fun. Or maybe you do because it's interesting. Anyway, so I want to talk about the GC and what it means. It means that if I'm writing code in C and I want to have a concurrent dictionary, welcome to a world of pain, like serious pain. To give you some context, in unmanaged languages, you have to deal with hazard pointers, epochs, or RCU, read copy updates, none of which works that well, all of which you're paying the cost for instantly, even when nothing is running. If you have one thread running and you have to have hazard pointers or epochs, you're still paying the cost of that. With a GC, there is something else that walks behind you and care everything, which means that you can make a really, really strong assumption. If I have a pointer to an object, if I can access an object, then it is reachable because I can reach it, and therefore I can do stuff to it. Compared to that, to C, where you get a pointer, you know what? You can touch that. I want to write, let's say that I want to write the following C code. Where do I have some C? Let's assume that I have and I want to do something like this. Now I'm in a problem because in another location in the code, I have this. And now it is possible that you got this value, and before you manage to add atomic reference, someone released that and freed that. And now you're trying to add an atomic reference to memory that was freed. That sucks. Now I'm doing a very high level explanation of that, but the whole point is that this is a serious concern. And in unmanaged languages, this is a huge issue. With C#, oh, this is what I have. And the fact that I exist and I can access that means that this has not been freed. And this sounds like a really small thing, but that actually has a huge impact. you will not see commonly used concurrent dictionary in C++. If you look at Rust, which is a really good ecosystem, you have something called crossbeam epoch, and that's basically bringing a garbage collection to Rust, because if you use highly concurrent code, you absolutely must have garbage collection of some kind. Everything else here is also exactly that, except maybe this, and that's complicated. And it turns out that you can use these sort of things really effectively. Here is a part of an ongoing process that we have right now in the code. Really deep in the bowels of Raven, we have a class called pager that deals with reading pages of data from file. Effectively, this is the file abstraction that RavenDB uses. And internally, we do something like this. This is absolutely horrible. By the way, this code was written a very, very long time ago. This is actually, okay, so we can go back a lot until we get to this location. And so this was actually written at around 2016 and haven't really been touched since. Now, why does it matter? Because this log statement is something that we cannot touch anymore. So if I have 10 threads trying to call this method, all of them are going to be serialized. For fun, allow me to show you something really, really nasty. Did you know, where are you? No, come on. Oh, come on. I hate that it does this. It always goes here. But anyway, the enter method, which is the lock implementation, would actually do spin lock. So if you have 10 threads, all of them hitting this at once, and this is really, the href is just basically just calling increment, then the whole idea is that this is super fast. So 10 threads are hitting this, stopping a line, and they're now starting to do spin lock. And it isn't stopped long enough for you to actually say, hey, I'm going to be stopping the thread, pausing the thread. So you're burning a lot of CPU cycles, effectively doing nothing, waiting on this lock. And that is one of the things that we care about. So instead of having this pager state that we call href and release, which is the standard thing to do, we are now moving to something else, which is this guy. This is a class, and this is a really interesting class because what it holds basically is the file and the memory mapping and whatever. But I want you to look at what happens here. Here we have a finalizer. So what we are effectively doing is saying, hey, I don't want to dispose of the state explicitly. I don't want to call release on that. I'm going to drop references to that and then ask the GC to do the cleanup for me. Now, in general, this is something that says, oh, this is weird. I don't want to put so much pressure on the GC. But state is effectively a file, so we have a very few of them. But the fact that I don't need to call this method for every single time that I access the file is huge for me because this is expensive. And this happens, whenever I close a database, insanely infrequently. Oh, sorry. Where is it? Okay. So, but at the same time, now I have a really, really big problem. Because remember, this effectively holds a file. I want to explicitly dispose that when I close the file, so I can, for example, delete the directory. So I cannot wait for the GC to complete. So now I'm able to do something like this. I have a weak reference to myself, and whenever I'm getting called, which is in here, then I'm keeping track of all of the live file that I have as a weak reference values. And if I need to dispose the file, then the pager is going to dispose all of the relevant files. But if I don't, then the GC already cleaned them for me. So this is a really nice trick in order to manage things. Okay. That actually counts for a lot. Again, concurrent code, concurrent collections, this trick of using files and weak reference to ensure both that I have predictable disposal and don't have to take references and locks is a huge impact. And now it's time for questions, and I think that there are actually a few of them already, so I try to answer those.
Yeah. Oh, go ahead, Oren.
No, there is something here about from Gabriel about how fast is this unmanaged code versus Rust. At the end of the day, everything is assembly.
Mm-hmm.
And I want you to look at this code. What you will notice in this code, there is absolutely nothing except a repeated set of the same assembly instructions. I'm able to generate super tight code that does something, and I'm actually able to process more than 1 billion entries per second using this method. Now, a lot of that depends on the sort of code that you write and what you're doing. I'm going to contend that I'm able to produce equivalent code in most cases, especially when I have the ability to optimize for the relevant pieces that are hotspots, because I'm able to optimize very heavily utilizing this approach. It's actually even more interesting than that, because Rust would have to pay all of the explicit cost all the time, or they would have to bring in their own garbage collection using crossbeam epochs or something like that. I'm doing, I don't know if you keep track of all of the things that happen in C# land, but there are a lot of small tricks that makes a huge amount of difference.
Mm-hmm.
For example, let's go and write this bit of code. Read only span. Okay, there's nothing really interesting here. Now I can do this. Oh, come on. So I want you to see something really interesting. Here you can see this is a call. This is a call to the stream method, the stream write method. What you will not see is a call to the name method. Why is that? Look at this value. Look at this value. Static is only span of byte, and I think maybe char as well, but byte for sure. Actually get stored as a static value by the compiler. So this just gives you a reference to a static buffer. And I can do things like this. Yes. And that's surprising. What I expected to do is that it will not do this check. This is weird. Oh, because it is 5. Okay. Sorry. So now see something really interesting. What happened here? This is known at compilation time because this is static. So now I can, this is a compilation time known value. I can just elide it out here. There are other things that you can do with those features. Some of them are frankly quite scary. At some point here, I have some functions. Behold this thing. What this thing does, this is a syntax for something called a function pointer, which is similar to a delegate in C#. Let's see what this actually do. And let's see this. Action. Read only span. Byte. I'm missing this. Come on. Okay. Let's do it like this. So what you can see here, I'm calling this, I'm grabbing from the parameter the location, and I'm jumping to that. If I'm looking at the IL, this would be a call method. Where's that? No, so I'm in the wrong location. Here. This would be a call virt invocation. So this does a virtual call, and now I can do something like this. Delegate, and now I have int void. Let me just do it like this so we can more easily see that. So I can see here I have a call I. Here I have a call virt. Where is H1? Here's call virt. And this calls to the invoke method, does a whole bunch of stuff. If I'm looking at the actual assembly for that, you can see the difference between those. And there's, if you look, I mentioned, I think earlier, I don't know if I did it live, but that the way that we look, I looked at the release notes for C#8, for .NET 8, and I was drooling over all of the things that you have there. And many of those things are stuff that you just have to read and understand, like the read-only span trick or those sorts of things. But once you start knowing them, there is a finite or relatively small list. So you realize that, I can look at this code, and again, I have high-level code that I can write, and at the same time, I can write super low level. I can control the physical assembly that I have. I have to admit that it feels really weird that I write in C# code and then look at the assembly instructions, especially when you try to doing that across multiple architectures, so ARM versus x64. But you get used to that, and that has an impact by a lot.
Well, let me ask you, there's a good question in there, right? Like, so you're clearly experienced, you have a lot of experience with .NET, but like, how did you learn these tricks? Like, where did your skill set come from? Because I see in chat people are asking, like, is there a course I can learn about all this low level stuff? And is it something that they can find on your blog, or is it something
I
that just lives in your head?
So I write about a lot of those in my blog. Most of
Mhm.
them, like most of those things. Let me see if I have it. Yeah. So my blog has a lot of stuff like that, and that
Mhm.
walks you through both the algorithm, how it works, something like that. I would post the there's a series of 10 posts about this, and just for comparison, you can see the sizes and this is the size. I don't have the numbers on performance,
Mhm.
but it's ridiculous. I think that we can do something in the order of billions per second. I had it somewhere, I think. So it's been a while. Can't find it. But basically, this talks about the algorithm more than the actual implementation.
Mhm.
For those sort of tricks, when we're talking about the how the JIT works, etc., there is CLR via C# book, I think.
Mhm.
But a lot of that is basically blog and knowledge and just looking at the code that other people wrote.
Mhm.
Uh, Especially if you start talking about high performance C#, then there are layers that you have to reach. For example, buffer use. So where is it? This is something like reader reusable. Here, here is something so stupid. This is a reusable string reader, and the only thing that it does, it implements the entire interface of stream reader, but it allows you to change the string that you're using. Why do I need that? I need that because I have something like this, and then I can reuse the text reader and pass you a new one. And now, this sort of code isn't magic at all. It just, you need to understand that, okay, the text reader here has a bunch of, where is it? It has a bunch of arrays. Let's see if I can find it. So somewhere around here, there is a bunch of arrays that are being allocated. And by reusing this instance, I avoid additional high-level locations. So that's like
Mhm.
one step of this. The next step is understanding how the GC works and what's going on there. After that is start thinking about what sort of work you're requiring the system to do.
Mhm.
And eventually you get to the point of, oh, I would really like it if I could avoid branching. Now, most of this is not actually limited to just C#. So a lot of the stuff that you would be relevant in general. So read about high performance code. There's a lot of resources for C++, for example. Then realize, C++ talks about fault sharing. let's see, cache line. So in this case, I have something that is dependent on the cache line, and I'm using that specifically to ensure that two concurrently stuff that are concurrently used would not sit on the same cache line at the CPU level. This is because I'm doing super nasty things here that require me to be separate. But the basic idea is that, okay, that's not something that is specific for C#. That literally is something that is, this is how CPU works.
Mm-hmm.
Yeah.
We have a friend of JetBrains, Matthew Cruz, who does a lot with like F# optimizations and things like that. And he gets down to like the CPU architecture level. It's really fascinating. But a question I have for you, you're kind of showing us a lot of code samples and optimizations. Like, how do you and your team at RavenDB determine what is worth actually investing and fixing and improving, and what are things that maybe are like not worth? Because we saw that method that you showed that had multiple link queries in it, and link is great, but maybe it's not as performant.
It is look, link is amazing.
Yeah.
Never ever use that for high performance stuff.
Yeah.
Because the point for link in many cases is to get a really fast output, but not to output from the developer, not from the system. And so this is. I hope you can see that.
Yep.
So I'm literally going like this. Okay, there is nothing. This is not important. This is not interesting. And I find the bits that matter. Let me see if I can find a
and
snapshot.
For folks watching, that's dot trace. So if it's one of JetBrains performance tools. So
maybe this. Yeah. So, by the way, it is incredibly frustrating that this is here. I really love the old UI. Yeah.
I'll let the team know. I know we're doing a lot with dot trace in terms of improvements for like faster profiling and stuff like that. So, but yeah, happy to take feedback.
Yeah. Okay. So here we have something that hopefully would be interesting. No, it's okay. So now this is interesting because all of those are things that I don't care about. Those are relatively slow, and now I don't see why I actually looked into that. Let's look at this as a good example. So we have a logger and nothing is here. I don't have a really good. I'm not seeing any good recent traces, but basically, you look at the trace and then you're saying, where am I spending the time now? Oh, I know what I can do. Let me see if we have here. So if I'm looking at the global values, I'm never going to see anything interesting. But let's go to, I think that query run is a good one. And let's look at this. Apparently here I'm looking at faceted queries. And this is super annoying. So you end up in here somewhere. And why is verify size off interesting? They realize, this guy, and by the way, look at that. If I'm removing this guy, then I'm removing, if I move that, then something that apparently here I'm running executed this, but this and this together, they are almost 40% of the total time of the system. So okay, so I need to figure out why this is being called and how it is called, etc. A lot of the times, this is basically run the profiler. It can be .trace, it can be something else, but this is absolutely something that you have to run because it will never be the thing that you expect. 100% of the time, you will have a. We saw cases where we have a super optimized piece of code. It was slow, and we optimize it further. And trivial as up, apparently we call that as a nested loop. And it was, it is an amazing performance. You call that, and it was under 10 nanoseconds per item. But you call it 10 million times, it's going to be slow.
Yeah. Well, I have another question here for you because I was, you had mentioned you're optimizing C# code and .NET code, but you mentioned the garbage collector a lot. In newer versions of .NET, the .NET team allows you to actually replace the garbage collector. Have you ever thought crazy enough to be like, you know what, we need our own garbage collector algorithm here?
Yeah, and okay, this is what I would have loved to have is the ability to say at the garbage collection level, I want you to allocate all of the memory in this location. I think that there is actually some feature around it now. Where was that? So you can force an allocate to be pinned. This is really nice. Again, those are crazy and really, really low level stuff that you care about. But there is a way to say, well, I don't know if they do that. This is the arena work that they're working on. So one of the things that is really, really common in web applications, in services, etc., is that you have a very well-defined scope of work. And most of the time the work is small enough that I don't want to do any garbage collection. I want you to run and allocate only from this location. And then I want you to just don't do garbage collection, just reset everything here. There are stuff that you can try to do to get there. There is arena work that I don't know have reached any particular level, but the issue is that this is really complex. For example, how do you cache in certain environment? Because I want to put stuff into the global memory, but it's just copied it from the local memory. And it's become really, really interesting this way. Especially because you want to do that in such a way that you don't have to be aware of everything. I think that for going back to how do you do those tricks are absolutely worthless 95% of the time. Because the underlying architecture that you have is sucky in terms of achieving that level of high performance. Now, remember, if you're processing 20 requests per second, that means that in a day you're processing 1.7 something million requests. That's a lot. Most top 1,000 websites will never see that many requests. The problem is that in terms of performance and latency, it's not 20 requests per second evenly distributed. Tend to be clumping and peaks, etc. Something that you might want to look at, which has a lot of really interesting information in a very nice package, is the billion row challenge. And the billion row challenge is basically, here is a CSV file with 1 billion rows in it, and do some sort of aggregation on top of that. And I think that it was originally offered for Java, but I think this is this one.
Yes, it's that one. Yep.
Yeah, and you can see how the behavior across all of those. The leaderboard right now is in Java. Do we have the leaderboard across languages?
I think you have to click through to each language to see their unique leaderboard because it's a fork of the repo. But
Okay.
there have been a lot of .NET community members who have tried and done pretty well, actually. So .NET is pretty competitive uh, in the space. So it's pretty
Yeah.
neat.
And the nice thing about it, if you read those sort of entries, first of all, which is absolutely amazing, by the way, this is the, you see, not that long ago, we were much faster than Java. I don't know if you're still faster than Java. This is, I wouldn't be, I wouldn't expect it.
We love PHP at JetBrains.
Yeah,
Don't
yeah.
disparage PHP. We love it.
I don't know. I absolutely agree, but I would expect it for this sort of high performance stuff.
Yeah,
But
yeah.
again, looking into this now, go and read those entries and look at the approaches they took for that. So if we look into some of those, most of them are going to be, oh, I'm not going to do any allocation. I'm going to do. So, okay, here is a struct with all of the relevant field. You can see that a lot of that is being specific about where I'm putting that. The nice, so you can see here is the cache line size, etc. And here is a map. And this is probably, yeah, so this is a hash map.
Mm-hmm.
And apparently this uses native memory, and I don't know why it does that, but I can make some guesses. And the nice thing about it, there are blog posts that detail all of those sort of things for you. And both for C# specifically and for other languages, because the challenge eventually is running on the same hardware, so you will learn mostly the same things.
Mm-hmm. Well, let me ask you one final question, and then we'll kind of wrap up. But you talked about a lot about .NET's evolution. You've been doing this for 20 plus years on the RavenDB code base. Is there still something that .NET or C# haven't delivered that you kind of still want or need? That would make your code base easier or help you solve problems that maybe are still challenges?
I don't like it when I break the debugger. uh, so I made some mess recently, and I wrote some code, and I'm running my test, and it will fail.
Mm-hmm.
Run it in the debugger, and the debugger crashes. That was super annoying. You have to reach up to lower and lower level debuggers in order to manage things. Stuff that would be really helpful that you run into is async machinery
Mm-hmm.
is so complex. It's really easy to make mistakes there.
Mm-hmm.
One of the nastiest things that you can have is, I have an async process that's not complete. I have an async process that has a timeout on it, and it does not complete. And the only way to figure out what's going on is to take a full memory dump, load it into a debugger, not a .NET debugger, a WinDBG debugger, and try to literally troll through memory, trying to figure things out.
Mm-hmm.
You know what? Here is something I would absolutely love to have. A nice way to get the current stack traces of a nice way to get the current stack traces of a process. So let me show you something. So this is RavenDB, and this is a live test RavenDB.NET. This is the live instance we have. I can go into this thing and hit capture, and in 30 seconds or so, I'm going to get a really nice visualization about what's going on.
Mm-hmm.
Okay, so, and you can see, and this is basically based on the parallel stack feature. I think that the first time I saw this feature was in 2008 MVC conference at Microsoft, MVP conference at Microsoft, and I was shocked. This was such a good thing. Now, that means that I can go and look into specific how many CPUs being used, what is the exact method that being used, that, etc.
Mm-hmm.
In order to do that, what I have to do is spawn a separate process for mine, which attached to mine as a debugger, pauses me, dump the stack traces, and then call back to me. Unpauses me and then go back to me. That's like changing the tire while the system is running. And I think in Java, it used to be the case that you can go to a thread that says, give me your stack trace.
Yeah.
But the fact that I have to go to such lengths to do this, and the fact that it is worth it in terms of the troubleshooting, monitoring capability that this gives me, is such a huge task. It's just,
yeah, I might actually have some good news for you. In our EAP, in our early access program, which is happening right now, if folks want to go download what essentially is the latest version of Rider, I believe we're introducing a task view that might give you the results that you're looking for. So check that out. I think it's in the current release, but don't quote me on that. Try it out. But in the early access program, there might be, but it's early access. There might be bugs, so I wouldn't recommend I would recommend a side-by-side install. But on that note, I think that's it really for the questions. So we can kind of start to wind down here. I really want to thank everybody in the chat. Great questions, great conversation. Thank you so much for being involved. I want to thank our guest today, Oren. As always, you have so much information, knowledge. It's awesome. If you want to learn more about JetBrains Rider, you can head over to jetbrains.com/rider. Check out our blog where our advocates, including me, write content on the regular for folks in the .NET community. It's a lot of good stuff there. Check us out on the social media channels. And if you're watching this on YouTube, be sure to like and subscribe there. I've already shared Oren's blog. There's 7,000 posts there. So if you want to catch up, start reading now, immediately. Put everything else on pause and just read everything there. Be sure to follow him on social media. And if you're interested in RavenDB, head on over to ravendb.net. And be sure to subscribe to their YouTube channel as well. There's a lot of good conversations. There's a lot of team conversations, which I really enjoy as well. So you can kind of see the inner workings of the RavenDB team. Highly recommend that. So on that note, this is where I do my YouTube-y thing. Thank you. If you like this content, be sure to give us a thumbs up. It really helps us kind of calibrate what kind of content you folks want. Be sure to like, subscribe, and hit that notification bell to get all the new content that we're producing here at JetBrains. On that note, again, I'd like to thank Oren. Always welcome back. It was a pleasure, an honor. And on that note, goodbye, everybody.